Right. Yeah. Welcome everyone to the second session of the day. We are very happy to have Siva giving the first talk of this session. As many of you might know, Siva has recently joined ICTS, so he's local, but he still retains his affiliation at ICI Bangalore. So he's from both the places. So Siva will be talking about survival of a string in random traps. Yeah, please, Siva, please.
Thanks for inviting me. This talk is joint work with Matthew Joseph and Carl Mueller. And I'll spend a quarter of the talk not on the question that's considered in the abstract and title. So the first part of the talk will be on random walks in traps. So I want to illustrate this to sort of set the problem up correctly and sort of give you an idea of what to focus on. So mostly the model basics are very clear in this setting, and the question also is clear. Isn't this? Then I'll give a glimpse of the proof techniques in this setting. And one thing I'd like to do is while doing this is to keep track of the constants and the exponents. So this is something that I'll encourage everyone to do, to keep track of the constants and exponents. Though I may not be precise in illustrating them, but then the second part of the talk, or the three-quarter of the talk, I'll discuss the stochastic heat equation. Moving in a field of Poisson traps. So here again, I don't know how the audience is set up in terms of background and expertise. So I might be a little boring, but I'll try and explain. I'll define the model precisely, explain the basics again. Then I won't be illustrating the proofs completely, but I'll try and at least illustrate how the proof in the random walk case fails or is not implementable, and what changes are required to do this problem. And a couple of things that will come to light. Hopefully we are right. Surprisingly little is known in this area. In this model, which we are not sure about, but our Google searches are so far revealing only so much. So our results are fairly basic and elementary. So, and you'll notice in the proof that so I'll be imprecise, or imprecise is the wrong word, but it'll become clear with regard to constants. So of course, I've thrown the word constants out in a sort of vague way, but it'll be clear in a second. Okay, that's the plan. So the basic model is so just think of a random walk on ZD. So and just for convenience sake, I'll think of it as a continuous time random walk. And let's say jumps at rate 1. And maybe I don't need simple or symmetric, but let's assume it's simple symmetric. that's the first piece of the puzzle. That is, we have a random walk moving in ZD. And let's say it starts with the origin and then it moves around. And what we'll do is we'll place traps in ZD. So I'll denote the traps by green, let's say. So the trap field, I'll start simplistic again to give an intuition of the technique. So I'll think of, for every point x in ZD, I'll think of xi x as Bernoulli. So every point in X, I'll go toss a coin independently of the orange part and all the sites. So it's IID. And I'll place the traps in this thing. And the interaction is the following, that the walk gets killed at rate walk when xt is equal to x, gets killed at an exponential rate, at rate, let's say gamma times xi of x. So that's the model. So there are three components to it. One is the random walk, the other is the traps, and the killing feature when the walk encounters a trap. And this gamma can be a positive real number. I'll also allow for infinity. So infinity means that the moment a walk encounters a trap, it gets killed. So these are called hard traps. And if it's killed at a certain rate, these are called soft traps, because in the sense that it can interact with the trap and still survive. In the hard case, the moment it hits the trap, it gets. So the key question one studies about these models is, will the walk survive? Or what's the probability of survival? So there are various ways of studying this question. One is you can study the walk for a given realization of the environment, or you can average out the environment and study survival of the walk. So in this talk, I'll focus on what's called the annealed survival probability. By this, I mean, we will look at the chance of the walk when we average out, chance survival of the walk, when we average out the environment and the walk itself. So here, so the clock takes an exponential rate. So e to the minus gamma times integral 0 to t xi of xs ds would be the chance that the clock doesn't tick. That's chance to survive. And we'll average it out with the walk expectation and the field expectation. This I'll call as my S sub t. I want to understand what happens to S sub t as t gets larger. As t goes. That's the question. So let's look at the simpler case to get the intuition of the model. Let's look at the case when gamma is infinity. That means the hard traps, the walk gets killed immediately. So one can immediately understand just in this Bernoulli case, you can immediately see that this is same as exponent of, let's say, p times p to the power of the range of the walk. Because the walk hits the If the trap is there at a site where the walk hits, then the walk is dead immediately. This is our probability to walk. That's not a hard calculation to check. Once you have this, then this is now very amenable for analysis now. One can understand how to work with this with ST given this thing. So if you look at this, it's an exponent, range is an exponent. So there are two competing factors, right? So one is the exponential factor becomes small when the range is small. That's one factor. The other factor is there's a cost for the range being small by the walk. So there are two competing factors, and you have to decide which one wins, or how to balance the two out. Let me do a simple calculation to show this. So I don't want to write. Maybe I can write here. So if you were a walker, how will you survive? So one strategy to survive is the following. This is a strategy. So I'll just call it the lower bound. What you could do is, you could first say that, okay, the walk will always stay in a ball of radius alpha t. The walk will always stay inside this ball. This radius is alpha t. So in time t, I ensure that my walk stays inside the ball of radius. Then I go and say there are no traps inside the ball. So all the traps are outside. There are no traps inside. There are two competing costs now. One is that the walk stays inside the ball. The other is there are no traps in the ball. That's one way I can ensure the walk will survive. So this is something one can easily do, right? So I mean, the survival probability ST is going to be at least the chance that the walk stays inside. So that one can calculate, right? The walk staying inside picture is just e to the minus t by alpha t squared. That's just by invariance principle that the walk stays inside a ball of radius alpha t. Then the fact that there are no traps in the thing is again it's exponential some constant alpha t to the d. That's the volume of the ball of radius alpha t. Having no traps there is some constant. Those are two costs that you have in mind. If you can find alpha t that balances these things out, you have a chance to solve. Now what you do is a little trick in calculus. You optimize over alpha, and you will get that this person is going to be at least e to the minus c times t to the d over d plus. If you want, I think the correct value for alpha is t to the 1 over. If you want a calculus question for this, alpha t is I think t to the 1 over d over. That's the minimizing alpha or maximizing alpha. That's one simple way of showing that the survival probability will decay at least. A lower bound for survival probability is e to the minus c times t to the d over. But of course, now since you're in ZD, you have a lot more tools available for this random walk. And the Bernoulli case, you can use a Fibon-Card inequality or large deviations for the walk to show actually this you can actually calculate this probability expectation. So it's the same as, let me write this down, infimum 1 less than equal to alpha t to t, I think C1 alpha t to d plus C2 t over alpha t squared. This is what you get. I won't go into the techniques of this, but this you can use Faber-Cran. I always forget the spelling. And this will actually give you the survival probability is of the order e to the minus c t to the d over d. That's a fairly straightforward calculation. there are two things I'd like everyone to keep in mind. One is that I have to calculate some sort of estimate on the size of the range of the walk to get this estimate. But to guess the estimate, there's a simple survival strategy. You clear space, you stay inside the space, and there are two costs competing with it, and that gives you the answer. That's how you guess the answer. And if you're lucky, the proof works out, and the bound comes to it. Couple of remarks before I move to the stochastic heat equation. This calculation that I have here, it works far more generally. Let me write this down. So this works, this exponent is the same as t to the DOD plus 2, works for a general psi. So you don't have to put Bernoulli, you can put a Poisson field or general psi. It need not be a random walk. You could use xt could be a Brown in motion. But if it's a Brown in motion, then you have to change your traps to be balls of size 1, which I'll explain in the next part of the talk. And the technique is at this step is to do this step is large deviations theory. So large deviations for the range. That's how we would work with the hard trap regime. The soft trap regime, the same techniques can be implemented with little nuances, but broadly, this is the picture. Keep in mind. This, of course, holds true even in the soft case, that this lower bound holds true. The moment you clear space, you stay inside, there are no traps, and the costs compete correctly, you're in business. Okay. And there's a vast literature for this, for random walks and traps. Ofer Zeitouni's book, the Brown motion and obstacles, contains a substantial overview of results and own problems in the subject. Wolfgang Koenig wrote a paper, a survey article in 2016, the parabolic Anderson model, which has this field covered of the random walk and the potential. And myself, Alex Drewitz, and Rongfeng Sun have written a short review of this, of random walks and traps. There we also consider when the traps also move. So that's the random walk picture. So as I go into the SPD part, the intuition should be from the random walk, how to think about this problem. To 12:10, right? Approximately. Okay. So that's the first part. Now I'll go to the second part of the talk. So let me first define the stochastic heat equation, how the traps are, and then we'll try and discuss various things here. Okay. So let's look at the stochastic heat equation. And, so I'll think of this, after I write the equation down to be clear, I'll think of this as a random string in RD. So here, so how do you think of this? So my domain of my function u is 0t, that's time, and space, I'll think of it as 0j. I'll explain, I'll think of a circle, but as of now, write 0j, taking values in RD. And UT solves du dt. So the heat equation corresponds to a string that's sort of moving around, and I'll put space-time white noise at each time point. So I'll try and explain to you what the equation means in a second. And let's say with some initial condition, let's say U0 is. And I'll think of my interval as a circle, so I'll identify 0 and j. Maybe I'll write. Just periodic boundary conditions. So du dt is the time derivative, Laplacian is the second derivative in space, and Wt is white noise. So let me give a short definition of white noise. So W is, to me, it's just a d-dimensional centered Gaussian process with the following properties. That is, as you said, distribution value Gaussian process. So you take a set A in 0t cross 0j, WA will be normal with mean in 0 and Lebesgue measure of A. And of course, for the Gaussian process, I need to do this and I define the correlations. I'm done. So the correlations are WB is just the size of A and B. So here A and B are Borel subsets of 0t cross 0j. So one can clearly see that if A and B are disjoint, then A and B is empty set. The covariance is 0, so they're independent. So the noise is different in different parts of the domain. Only on intersections they'll have a sort of. So one way to think of a solution to this equation with this sort of random disturbances at each time point, I'll think of it in the mild form. So I'll think of UTX as integral. Always forget this. Okay, right. J pt minus s x minus y your y dy. Maybe I'll call it G here because it's periodic boundary conditions. Plus, so this will just solve the heat equation. But I have a random noise to it, with a random measure. So all I have to do is 0 to j, 0 to t. I'll have dt minus s, x minus y, w of. So maybe I should write it in this fashion. Integral 0 to t of w of ds dy. Where G solves the heat equation. Where G solves the dou T Gt is Laplacian by 2 T and G0 axis. That's how you want to understand the solution to stochastic heat equation. So there are two terms there. The first term is deterministic. So that just corresponds to what the heat equation is doing. It's deterministic. The second part is stochastic integral, because this is a measure and you're integrating random measure. So it's a stochastic integral. So this is historically done first by John Walsh. Very good set of notes. So John Walsh stochastic integral. There's a way to set it up. to do this whole equation. But formally speaking, you think of it as in d dimensions. You think of u as a string like this. That's how u will look like, moving in space. So I'm joining the point 0 and j, and the random disturbances at each point. This is how you think of the picture. So now I'll sort of try to go a little bit. There's a lot of notation involved. So I set the notation up on the board so that it's there for everyone to see again and again. Because in a slide, you have to keep going faster and faster. And, 20 minutes, I think should be okay. So the equation that we've already seen. So the way to think about it is you think about it as like a random string. It's moving around in space. So now I've defined the model. So again, I've said what A is. So A is A and B are Borel subsets of 0T, 0J. And this is how I'll think of the solution. This is called the mild solution. And there's two parts to it. Like I said, this is the deterministic part, and this is the stochastic integral. And G is the fundamental solution heat equation. So G is just the typical Gaussian kernel on, if we think of it, R plus clause R. But if I have 0J, I have to work with the boundaries a little bit better. So what's the traps? So the string won't see points. So but traps have to be a little bit larger. So I'll have to put traps in RD at rate nu, at Poisson clock nu, and balls of size A. That's how the traps will look like. Single points like I have there. Again, I'll do the same thing. It'll get killed at a fixed rate gamma, let's say, or hard killing, which is it. So this is kind of the picture that you should keep in mind. I have the string is the black is the string. So let's say U is the string. And the traps are the orange people. You can have funky things like this. That is, in a random walk interacts with the trap if it goes on it. But a string is d-dimensional. It has a different topology to it. The trap can be sitting inside the hole formed by the string. Of course, it will never look like this, but these are possibilities that I keep in mind. The string is typically very coiled. It won't be as loose as this. So if you're familiar with the trap model literature, the quench problem is infinitely harder than the anneal problem because of such topological issues. That there's trap inside the string somewhere hanging around, which will affect the behavior of the string. Because in the Brown and motion case, you can look outside and you're done with it. The string, you have to look a little bit more. So I have to set up the trap model precisely. So I'm just doing exactly like the random walk case. I'm not doing anything fancy. Just notation is a little hideous, but so what you'll do is typically is that you'll define a potential around every trap. So just for our sake, we can always think of H of X as just think of it as gamma times indicator of the ball of radius A around. That's how you can, that's one example of H you can think of all the time. That means I'm just doing this trap. I'm just putting a trap with size A. So this size. This is some point, let's say Xi1. The example. So, and then to just the Saval probability is exactly given by the expectation. of V of U of S, X, comma, psi. So it just defines the interaction of U with the random trap. And this again is the annealed expectation. So here I will just make note, I'm just always averaging out the psi and the U as well. So it's the product measure. That's what I meant. So again, what are the main results? So I will show you the main results. It's sort of a little anticlimactic in some sense. For the j equal to 1 case, that is when I standardize the spatial domain, the survival probability of the string given the potential h, I'll just write 1 here, and then the Poisson field as v. Maybe I'll just draw a different color. This is of the order, you can show that this is of the order e to the minus some constant times e to the same as the Brownian case. So that one can show that the survival probability when string size is 1 is the same order. So one intuition one can have is that if you go back in this picture very, very far away, the string looks like a point and it's moving like a Brownian motion. So survival probability should be the same as Brownian motion, and that's why the exponents match. The proof doesn't go that way, but that's probably one intuition. For j bigger than 1, alas, the statement is not true. We have an incomplete result, which I'll show in the next slide. So j bigger than 1, what suddenly happens is there's an interplay between t and j. Which is expected if the string is quite large. You need to go further and further in time to get the correct exponent, and vice versa. But the exponents don't match. The upper bound and lower bound don't match. So I will show you in the next slide. So what we'll be able to show is that ST of H J nu, this on one side, okay, the exponent in T will match, but the dependence on J, you will see, is not satisfactory. What we'll do is we'll get this, and we'll get on this side also, we'll get e to the minus c tilde of J, and the exponent in T is the same. So these are the two results I'll give you in intuitive English language. The next slide, I'll present the precise statement of the result. But the crux of the matter is that C tilde of J and C of J don't match in the exponents in J. Okay, so they sort of differ. And that's not quite satisfying, but that's where we are. It's sort of in exponential scales. And why is this? I'll explain in detail as I do the proofs in the last 15 minutes, is that in the random walk case, see, to do these things, you have a lot of tools. Potential theory is available to you, the Laplacian, you have the spectral analysis to do things. You can work with this. But sadly, in the infinite dimension setting, such techniques are not available yet. One has to really work hard from basics. So here's the result. So in the hard trap case, the lower bounds of the hard trap and the soft traps match because the trick is the same. You clear space, you stay inside, you have no traps inside. And when the two costs match, that'll give you the answers. That's why these two things match. There's no problem. Sadly, in both the hard and the soft, these two don't match. There's sort of a J factor coming in. And of course, this is okay, it's not so bad, but this is sort of disappointing. But that's where we are at. We're not able to get T. It would be nice to get T over G on both sides. But we think we think we're losing a lot in the upper bound on certain days. On certain days, we think we're doing a too crude lower bound. We're not sure which one is the correct answer. Very nice. So that's the result. So of course, this factor is there in the soft trap case, but that's just an artifact of the proof. This is not so worrying, but the worrying factor is that J squared on this side and J on this side. But that's the result. So there's an interplay between T and J. And you can also, I haven't said in the theorem in the slide, but in the paper, if you go look at it, we tell you how far you have to go in terms of J. It's a power of J you have to go. I've just said large enough T here. And these constants are independent. Very good. So one trick always does in SPD is scaling. See, it's a very powerful tool in SPDs. So you can always scale space out to unit length. And everybody works with that. So one can think, okay, I'll scale the problem. I'll work with the scale problem. I'll get the exponents because if you look at J equal to 1, the exponents match. I'll scale J equal to 1 and then I'm done. So how do you do this? You take U, you define V with the correct, you have to scale space by root J, you scale time by J squared, and space inside by J. If you do this, then you shift the heat equation, stochastic heat equation, to domain between 0 and 1. So J factor is out of the picture, but the time also scales, TJ. Of course, there's also white noise, space time, but it's independent, some other different white noise, but it's also space time white. So same heat equation, I have removed the dependence of J in space. Of course, the time factor, that's this time. That's not really an issue. So I can work with V. I don't have to work with U. So that's one way you can think is a trick to get from general J to J equal to 1. But if you just notice a little bit, you pay a price for this root J outside. So that's scaling RD. You scale RD by J to the minus half, you're affecting the Poisson points and the radii of the Poisson points. And that will come in the exponent constants. That's what so just make precise. So you look at this, you have I've written the same thing on both lines. That's okay. So I have to go here. I have to go here, and I have to just replace this S by J squared S, and X by JX, and I have to divide by J to the 1/2, right? And I have to multiply by J to the 1/2. That's how I have to scale appropriately. It's a change of variable I have to do. So when you do this change of variable, what will happen is that everything will change. You will get expected value of exponent of something here to Tj to the minus 2. That's okay. You get 0 to 1 here, but you get a V tilde and a V inside and a Xi tilde. So that's what will really damage the whole calculation. So you will not preserve the same noise, same Poisson points, and the same radius. So everything will change. The time will change by this factor, the field will change by this factor, and the Poisson points will change by this factor. Then whatever calculation you do for J equal to 1, your constants will appropriate or multiplied by those factors. And that's why the J constant is not the same. So scaling will not immediately do the whole job for you. It'll be a little bit more. If you want independence in J, it'll be a little bit same constant in J. It'll work a little harder. Looks like it. But this relationship you have. So from now on, I can work with this J equal to 1 case, and whatever I have, I'll transfer it back to the general case. And all the constants will suitably multiply across. Very good. The last 8 minutes, I'll sort of so I'll try and show you the strategy for the lower upper bounds for J equal to 1. We'll use scaling for J bigger than or equal to 1, and we'll chase constants using scaling relations. That's the proof. And the artifact of this method is that sadly the upper bounds and lower bounds don't match. And that's the price you have to pay. So the lower bound strategy is exactly the same. What you do is you try to create a space around the string with no traps, and all you do is you have certain costs having no traps. You have certain costs of having the string staying inside the ball, and the costs match, you're on your way. So it's not hard to do this, but you can't do it like the random walk case by an invariance principal argument. You have to do a well-known decomposition of the string. Maybe I'll skip this slide. I'll come back later if I have time. So what you do is you split the string up into two parts. So you have the string, which is U, and then you have what's called the center of mass of the string. The center of mass. And what's left is what's called the radius of the string. So this is a standard trick that algebra trick that since your integral 0 to 1, UTX just is a constant, so this is just UTX, and XT matches with this side. So this is an algebra trick that you can split UTX as some integral which can be controlled by the radius of the string and XT. That's how you control how the string will move in space. And it's well known that the center of mass is a Brownian motion, so you can use results from earlier on in life. And you can also show, because I'm in the Gaussian setting, I have XT is independent of RT. I have independence of the radius in the center of mass, I can work with that to get there. So that's how to resolve the lower bound immediately. So all you do is you have no traps in a ball of radius alpha t plus 1. The center of mass stays there. Your radius also is small enough. You have all these three pictures, then you know that this picture happens. So once you do this, you do the same calculation again, you optimize over alpha t, and you get the lower bound is of the same order. So this is a order 1. This one can show that this is a order 1. That's what the small ball result was about, but I'll go back to that later if I have time. So that's the lower bound idea. But now the upper bound is what's the harder part. There's no potential theory, there's no spectral analysis to work with. You have to go back to the basics of the string. You can't do any Laplacian and LDP to get this idea. So here's where we give away a lot, I think. So one immediate calculation we did, like we did for the random walk case, is that the string survival probability is essentially the volume of the sausage of the string. Because if the sausage around the string of size A has no traps in it, the string will survive. So it's the same calculation like the range calculation. So in the hard trap case, the string survives if it avoids all traps. Avoiding all traps means that you take your string, let's say you take your string like this, let's say, and then you take a sausage around the string of size A on both sides. This whole piece should have no traps in it. Only then the string will survive. So all the pink region should have no traps. So now, once you do this, then it's a simple calculation to show that this equality holds, just by the same idea like we did the Bernoulli case. So now you're in business. If you get a bound on the volume of the sausage SPD, you're bound on survival probability, the hard trap. Surprisingly, this is not known, even in the Gaussian case, like in this simple setting. And we kind of guess why it's not known. It's hard for us to do, but so a lower bound on this volume will imply an upper bound on survival probability. So how does one do this? So again, you do the fact that that U looks like the radius or some integral form of radius plus the center of mass. And what you do is you have to collect lots of volumes of the sausage because you need a lower bound. You need lots of sausage volume. So what you do is you try to construct disjoint pieces of the string that will contribute independently to the volume. So for example, like I know the volume of the sausage of the string until time t is at least this volume plus this volume, right? For sure. But here I have to be careful because the intersection, I can't take this volume and this one. So I have to make sure I can go further and further in time. In 0t, I get independent pieces of the string to count the volume separately. And once I do that, I have a lower bound on the volume. How does one do that? It's kind of a cool result that the center of mass is Brownian motion. So you can go back to the Venus sausage result. So xt is a Brownian motion. That's a result that's known. So you allow for center of mass to keep moving further and further away, at least distance lambda from all the previous tau i's. So you look at the first time it's moved distance lambda. Look at the next time it's moved distance lambda from everybody else before, and similarly again from everybody else before, and do this. Then you can do a large deviation calculation to show that the crucial bound, that there are at least so many points in 0t. So there's tau 1, there's tau 2, and so on, there's tau n, and so on and so forth, till time t somewhere here and 0 somewhere here. There are enough points where the center of mass moves further and further away. That's the first step you do. Then you're almost in business. All you have to show is that you collect enough volume. All you have to show that each of these places, you collect enough volume. You collect at least a to the d volume, approximately. This is what I've written precisely here. But alas, the string is correlated because it's an integral, right? It's an integral equation. It's correlated. It's not independent. So you just can't say I'll add up these volumes at these tau i's because they'll all be interconnected, and they're not independent as well, even if they're far apart. So to work a little harder to show that there are enough points first. That's what I said. There are enough points for this at this exponential scale, and this I explained to you just now. And you have to show that you can use the repetition of the string to show that if you go far away, you make the deterministic part very, very small, and only this part matters. And this gives you the essential independence across far away. But then you have to show now that there are enough tau i's that are far apart to give this calculation. So to show that these things happen, there's a tau 1 right, the tau I right here, and I can wait for long enough. So sausage disband itself, and I have a tau j. The two sausages don't intersect each other. And then I'm done. Once I have this, then I look at the number of tau i's, I multiply the volume of each sausage, and I have a lower bound. That's the idea. I'll just conclude with what's left to be done. Lots to be done, I guess. Matching upper bounds for sure. Can I drift to the SPD? Multiplicative noise. The Quent's problem is very interesting, even in the Gaussian case. And of course, the traps are moving is a very fascinating question. Thank you.
Yeah, maybe we can take one quick question. All right. So maybe I had a quick question. So what is the speciality about your assumption that you identify the endpoint?
Oh, it's just periodic boundary conditions. If you don't have that, you'll have a different kernel and you'll work with that.
It'll be the same. So it doesn't have to be, I mean,
I don't want to say it will be the same. You have to work with it and show it. But I think it should work.
I see. So it doesn't have anything to do with that the image is not simply connected or something like that.
No. There's no geometry involved yet because I'm not doing the Quent setting at all. I'm just averaging everything out.
Okay.
There's no, only heat kernel will change. You have to work with different heat estimations.
We don't really have a break. I mean, we'll start in 2 minutes. So as however long it takes for the next talk to set up. So we'll start at 12:15 with the next talk.